feeling really one with nature now. I myself hugged a dolphin, which I believe has only vestigial limbs. Is that right? The flippers. Anyway, Nils is going to tell us about robust, simple models for legged robots in 6 minutes.
Hi, everyone. Can you hear me? Looks good. All right, so I'm going to talk to you guys today about some pretty early stage work. So if you have any feedback on this, I'm really open to it and be happy if you have some ideas for me. So this is some work I've been doing with David Remy and Ram Vasudevan, and it started from the work we were doing last year, trying to generate guaranteed safe controllers for legged robots. And one of the questions that came up from Chris actually last year was, can you ever produce any kind of guarantee from a model that translates to hardware? So can we take this high fidelity model that should be moving in the video and use it to make a claim that our hardware is not going to fall down? Now, this is in general challenging. So we can look at the dynamics of the robot. Let's say we have some model of the robot. So we have x dot is some function of x and u. We can say this is safe in this region, which means that for all points in the green box, it's going to stay close to the origin. It's not going to escape. And this sounds great. Now, let's say our model is actually pretty good and it fits our data pretty closely. And these blue dots are evaluated derivatives from our hardware. Can we say that now our hardware is safe with the same margins? Well, if we take a point on our state space and we say, oh, look, there's a derivative here that we found that was negative, well, this point is going to escape, and it's not going to be stable. And so what that means is that even if you have a very good fit of your model, stability is a very tricky thing to reason about if you don't address the error in your model and the uncertainty in your model. And really, this is an approximate model. So what can we do instead? So one way that we're thinking about this problem is we choose a disturbance function, and we find a disturbance function that bounds essentially all the observed data that we have. And what we say is that our dynamics can take on any value within this purple set. And since all of the points that we've observed lie in that purple set, now if we can make a claim about the safety of the purple set, maybe we can make a claim about safety on the hardware. And that's the idea here, is that if we can claim that for all possible dynamics in this set, we stay safe, then maybe we can make a claim about robot safety. So what does this look like? So if you look for all points in this green region, here all the points we've observed have positive derivatives, so we're going to move to the center. Here all points we've observed have negative derivatives, we're going to move back to the center. And now even though we don't have a perfect model of a robot, we don't really know what it's going to do, we can still say that maybe this is a safe robot or a safe controller. And this is illustrating what I just said. So the problem here is you think, oh, this is great. I can find a disturbance that bounds all our data. Let's just make a big box. Let's just say we can take values from all over. Well, if your disturbance model is too big, you can't make any claim about safety at all because this model can really do anything. So from here, I can go right, I can go left, and I can't really make any decision about safety. So that's really the game. We want to find something that bounds all of the observed data, but isn't too large. So this sounds great. We take our simple model, or we take the model of the robot that we have, we add some disturbance bounds, captures all the behavior of the robot, we're done, right? Well, the problem is this is a pretty complex model on its own. So this model has 22 states, it has 4 inputs. The tools we're talking about using here have closer to 4 states. And that's a really big margin, because we scale poorly with state dimension. So our idea is that we want to take essentially the lead of the biologists and say, let's reduce our behavior to the simplest model that exhibits our desired target in terms of stability. And so this would look something like maybe a compass gate walker for the robot shown on the left. And now this is something that we can work with. Of course, we have to do the whole same process, and we have to make sure this compass gate walker covers all the behavior of the robot. And this looks like a simulation relation. So if you have your robot with the full state space, a lot of states, a lot of inputs, you have our template with few states, few inputs, we need to define a mapping that takes the states of the robot, maps them over to the states of the anchor or the template, and we need to define a controller that takes the inputs of the robot, maps them to the inputs, or inputs of the template, maps them to the inputs of the robot, and there's some flexibility here. So if we can define a simulation relation between these two, then we're happy. That's more or less where we're at. So these are some of the ideas we're working on to improve it, and thank you, Chris.
Thank you all very much. Okay. If that next speaker can get their computer going, and let's have some questions. Okay, I'll ask a question.
Okay.
Even the toothpaste around your data,
Yeah.
isn't that way too conservative?
Hopefully not,
So how will we know?
by putting it on a robot.
When will that happen?
Hopefully in the next few months.
Excellent. Another question. Yeah, okay, the cube of happiness, go. It's dead, Jim. No. Stroke it.
Yeah, you're getting there.
Oh, just stand up and shout.
All right. So for sufficiently interesting behavior, do you think it will be possible to ever prove safety, or that, like, so for sufficiently interesting behavior, do you think it's even safe in the first place?
For sufficiently interesting behavior, do I think it's safe in the first place?
Yeah, so like if you have a robot doing more than just kind of slow walking on a treadmill, walking over really rough terrain, falls are going to happen. Is it useful for a robot doing stuff like that to try to prove safety?
I think so. We're going to start with the less interesting behavior and kind of work up to there. But
Okay.
I mean, we do pretty interesting behavior without worrying about falls that often. So I think there is some possibility there. We good for time?
No, because
Yeah.
they're halfway off the thing.